Welcome back. The other kind of compound event that we usually like to deal with is called mutually exclusive events. This is concerns probabilities that involve the word or. Well, we say that two events are mutually exclusive if the occurrence of one means that there can be no occurrence of the other. If A and B are not mutually exclusive, they're said to be conditional. In this case, please bear in mind that when we say mutually exclusive events, this is not the same as independent events. In independent events, A occurs and B must occur at the same time, and if both of those occur, right, one does not affect the other. Mutually exclusive events means that one event necessarily precludes the other one from happening. Well, there's a rule right here, and a good illustration of this uses Venn diagrams to help us put this together. Sort of the intuitive definition, though, if we think about it, says this: if we want to find the probability of A or B occurring, and remember that means that event A can occur or event B can occur or both, then we would find the sum of the ways that A can occur and the number of ways that B can occur, adding in such a way that every outcome is counted only once. So the probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. Well, there's two ways that we can get mutually exclusive rules. If the two events are mutually exclusive, right? If the total area is 1, the probability of event A and the probability of event B, if the occurrence of one excludes the events of the other, right? Then they would simply just add those two probabilities together to get a total probability. But if they are not mutually exclusive, that means there's something that they have in common right here, right? So we have to be very careful in the way that we count these because we might be counting some probabilities twice. So this is a non-mutually exclusive or conditional events here in this first case. And let's talk about how we get these events. Formally, if events A and B are mutually exclusive, then we can talk about the probability of A or B being just simply the sum of the two probabilities. If we think about an event such as we count the number of families who have no children versus the number of families who have one or more children, right? Those are mutually exclusive. Either you have children or you do not, and formally, the probability of A or B would just simply be the probability of both of those added up. But if events A and B are not mutually exclusive, then to get the probability of A or B, what we're going to do is we're going to add up the probability of event A and the probability of event B. But since they overlap, we can't count this area in orange twice, so we have to subtract the probability of A and B. A contingency table is a statistical table that shows the observed frequencies of data elements classified according to two variables, with rows indicating one variable and columns indicating the other variable. Right? These are really good contingency tables for helping us quantify how to calculate something like a conditional probability. And let's explain how this would work with an example. In this example, a company surveys its employees to determine their health care benefits along with the number of dependent children, whether or not there is a dependent children, right, in their family. So what is the probability that an employee chosen at random had either subscribed to an HMO or had dependent children? Well, it's an interesting question. This table would tell us, and we see that, for example, in the first column, where we have HMOs, 145 of those had dependent children, 39 had no dependent children, and a total of 184 employees had HMOs altogether. If we go by row, we can see that dependent children, there were 145 of those that had an HMO, 85 had Blue Cross Blue Shield, or they didn't have any health insurance at all, for a total of 253 employees who have dependent children. But what's the probability of both of those things happening? And or, right? A or B, right? Well, here's the way that we're going to do it. First of all, we can say, well, how many had an HMO? we know that the probability of randomly choosing an employee who subscribes to an HMO is 184 out of 386 total employees. So 0.4767. The probability of somebody having dependent children out of all of our employees is 253 out of 386. Right away, we know that these two are not uh, independent. We're not mutually exclusive. And the reason why is that if we try to add up these two probabilities right away, let's look at what happens. 0.4767 added to 0.6554 gives me 1.1321. The problem with that? Well, remember that all probabilities must be less than 1. We can't get a probability that's greater than 1, so we're counting something twice. So the question is, what is it? Well, it's these people. Here are people that have both HMOs and dependent children. There's 145 of those. So the probability of subscribing to have an HMO and having dependent children is 145 out of 386. Using a Venn diagram to illustrate what's going on right here, we can see the following. We have 184 employees that subscribe to an HMO. We have 253 that have dependent children, and 145 of those are being counted twice in this survey. So, in order to account for that, we want to take the probability of H or D, being the probability of H having an HMO, plus the probability of having dependent children, but subtracting the number who had, or the probability of those who had both dependent and HMO in their background, so that we don't count them twice. So that's 184 plus 253 minus 145 out of 386, and that gives us a probability of 0.7565. Well, that's what we want, and that's our answer, and that's our example of how we use that addition rule. So to wrap up, don't forget that this week's assignments that are due by Friday of the third week, you're going to watch Chapter 3 lecture and complete the Lecture 3 form for attendance. And by Monday of week 4, you should have completed the Chapter 3 WebAssign homework and posted to Discussion Board 2. Have a great week, everybody. I look forward to reading your posts in the class.